IntelliQuest Incorporated, and held client-side research positions at Boehringer, Mannheim Diagnostics, and Boehringer Incorporated, and a management consulting position at ZS Associates. Ladies and gentlemen, please welcome Keith Chrzan.
Okay, can you hear me? Hi, I'm Keith. I'm going to talk about situational choice experiments. I'll tell you what those are, and about some alternative ways of analyzing them. Okay, so by way of outline, I'm going to explain what these kinds of experiments are. I'm going to talk about the standard way I've analyzed them over the years, which is to use an unconditional logit model. I'm going to talk about some alternative models that I've tried or that I want to try. Classification trees, random forests, and something called catboost. And then we'll do some empirical comparisons. Talk a little bit about the data sets I'm going to use for those comparisons, some cross-validation results about predictive validity, and some results about how well these models do in terms of explaining what's going on. Because I'm a marketing researcher, so my clients are, for these kinds of experiments, are typically pharmaceutical companies who want to understand how physicians are making prescribing decisions, or they're academics. A couple of the data sets have to do with decisions that get made in nursing homes about how patients are treated. So oftentimes understanding what the models are saying and how they're prescribing different behaviors is important to my clients. So here's a typical example of what disguised a little bit here, of course, but a typical situational choice experiment might have 10 or a dozen questions like this. So we've got a description of a patient here. This is an elderly female patient with a certain body mass index, and some other facts about her. And for this patient, we asked the physician what they would prescribe to treat some dread disease that we're studying. Would they give the patient an aspirin, an apple a day because we know that keeps the doctor away? Maybe the patient just needs to chill a little bit and have a good stiff drink or some laughter or electroshock therapy. So obviously this is a silly made-up example. Typically we would have our client's drugs name in there and some competing drugs, but you get the idea. Excuse me. So we've got a patient type there that's experimentally designed. And then we've got a multiple choice response. Again, each respondent answers 10 or a dozen of these questions, and the patient characteristics conform to an experimental design. That's why it's a situational choice experiment. Excuse me. I typically use unconditional logit, which if you read the literature, you might also see it called a polytomous logistic regression to analyze this model. The result is a utility function for each level of the outcome variable, using one of the outcomes as a reference. It's readily available in various software packages, and it gives me, in addition to a statistical model with standard errors and odds ratios and stuff that my academic clients like, it gives me choice probabilities by way of what's called the logit choice rule that I can build into an Excel simulator. So for my commercial clients, I can hand them an Excel tool and they can manipulate those patient characteristics and see how the physician's choices are changing. So this is just a little example of what the output might look like here. I get a vector of coefficients for each of my levels of my outcome variable. I use one of them as a reference level, and then I have a set of these utility functions, one for each other alternative, and one for each level of each experimentally designed variable in my questionnaire. mentioned that these utility functions, we can use them to predict the probability of choosing some outcome I from some set of outcomes j by exponentiating the utility of alternative I and dividing by the sum of the utilities of all the alternatives. And that utility function there is just a linear function of the coefficients on the previous page times the x's, the variables that are that describe the particular patient in question. On occasion, my clients want to segment the patients. They want to understand the decision hierarchy that the physicians go through in making these decisions. And a natural thing to do there is to put together a decision tree. So just trees, these kinds of trees are what are called recursive partitioning. And recursive just means we're going to repeatedly apply a rule, and partitioning means we're going to keep dividing our sample into smaller and smaller pieces. And I'll show you an example in a minute. There are also examples of supervised learning models because they're supervised by the dependent variable, in this case, the choice of therapy. So here's a tree example. Anyone from Australia? Okay. Just in case it ever comes up on a trivia test, that is a southern Corroboree frog from Australia. And I'm using this example because I found this nice little data set on the internet. It's a set of geographic predictors about whether in a certain location in New South Wales, Australia, you find these frogs. And it turns out that whether you find these frogs might be a function of their latitude and longitude, their geographic location. It might be a function of altitude. Maybe whether you're in the lowlands or the highlands might affect the presence of these frogs. The number of nearby ponds, because of course frogs breed in ponds. The distance to the nearest breeding pond, some rainfall metrics, and some other variables were in this little data set. And so I ran a decision tree model and found this, that our total sample of 212 locations, the first most important predictor was how far the location was from a breeding pond. If it was pretty far away, more than 624 meters, only 20% of those locations had frogs. If it was closer, less than 625 meters, 68% of the locations had frogs. And then the second most important predictor was the amount of rainfall. So if it was a relatively dry area, relatively few frogs. If it was a relatively wet area, relatively more frogs. Okay, so that's how a decision tree analysis works on some silly frog data. There's different kinds of decision trees. There's classification and regression trees that date back to the 1980s. There's more recently something called conditional inference trees that correct an important bias that the traditional cart trees had. The cart trees used a measure of purity, the Gini index, to form those splits, and then it pruned. After it built a complete tree with lots of splits, it used a complexity parameter to decide how far back to prune the tree. The conditional inference trees, they use a multiple comparison testing procedure to decide how many splits to keep making. Some other analyses I haven't used for this kind of model in the past, but that I read about in the literature were random forests. Here we're going to grow a large number of trees, each one of which uses a random subset of respondents, and at each potential split it uses a random subset of the potential predictor variables. And those two types of subsetting are said to decorrelate the tree and reduce the collinearity problem that's common in trees. Another neat thing about random forests, it also gives us importance measures that we can report to our clients. And we can even combine the conditional inference trees from the previous page and build a forest of conditional inference trees. And that's what we actually did for this research. So the idea of building a forest is, instead of just one tree, the correlation problem with one tree is that, let's say we're doing a study and we have a variable for income and a variable for education. Well, very often those are both correlated in real data sets. And in a tree type situation, It could be that the first split happens on education, and education's eaten up most of the variance that income could have explained. So income won't come into your tree, even though it's potentially an important predictor. In random forests, at each split, we're only going to consider a subset of the variables. So we might be considering income and not education, and so income's allowed to split to contribute to the first tree, and maybe income doesn't even come into the second tree. And so but across a bunch of trees, some of them are using income as a predictor, and some of them are using education as a predictor, and they're both getting their say. They're both contributing to the prediction. For using a forest for prediction, we just run each of our cases through each of our trees, and there might be hundreds or thousands of these trees, and each tree gets a vote about which, in our case, which therapy the patient's going to be given. So when I went and looked at the literature, I found that recently other people have been applying trees to choice models. There's a paper by Bach in 2019 where he says decision trees tell better stories than binary logit models. And in one particular experiment that he looked at, the tree predicted better than the logit model. Brathwaite et al. In 2017 wrote a nice paper. They said, you know, if you think about if you try to think like an economist, trees are kind of neat because they can uncover non-compensatory choice processes. And in the course of making all these splits, they could identify non-compensatory choice processes. Instead of, you'll notice from the logit equation, we've got a linear function there for the utilities, essentially a compensatory model. You could do badly in one attribute and well in another and still succeed. But real markets might not be that way. In real markets, some attributes might be product killers, and you can pick that up with a tree in a way that you can't with a linear model. So he said, you know, these trees also make good sense from a microeconomic standpoint, and in his cross-sectional data set, he found that a tree outpredicted the logit model as well. And then two more papers used cross-sectional models. One was reporting travel mode choices in Delhi, India, and the other one was using behavioral data from flight bookings, and they both found that random forests did better than logit models. So trees and forests look pretty promising as ways to model this data for the reasons just cited. They've been found to predict a little better in these papers. They fit better with microeconomic theory. They allow non-compensatory choices. So what I wanted to find out is, those studies all used cross-sectional behavioral data. But I'm not dealing with cross-sectional behavioral data. I don't have to worry about collinearity because I'm using an experimental design. I don't have any collinearity. So, you know, do we need to go through the trouble of these more complex models for modeling the kind of data that I've got? As well, so I had seen my friend Joe Retzer present a paper at a conference in the spring, and he used something called XGBoost. And I thought, oh, that might be a neat addition to this paper, so let's look at XGBoost. And XGBoost is a kind of boosting, and the way Joe explained it to me is, you build a tree, and then the errors from the tree that you built go into, they're the constituents of building the next tree. So with each tree, you're making less and less error in your predictions. And it's called extreme gradient boosting. It's kind of a neat thing. It's a neat method of making tree algorithms even better. It scales up to really large data sets. Most of mine, as you'll see in a minute, aren't huge data sets. They're based on survey research where we have hundreds or sometimes thousands of respondents, but not necessarily a lot more than that. And as Joe looked into XGBoost and thought about my particular problem, he said, you know, there's an even newer method called catboost. And the benefit that catboost here, the big benefit is that it's really made to handle categorical variables and categorical dependent variables, which is what I have. I have which of 5 drugs are people going to recommend. On the other hand, there's some downsides to it. The particular one that Joe discovered was that the model is slower to train, and model exploration is a little bit more difficult. So in the time that it took me to run the logits, the trees, and the forests, I was done with all of that before Joe was done with about half of the catboost models. So they were a bit time consuming to run. And the way we did the cross-validation is we used the Caret package in R. Caret is a package that's set up to allow you to estimate the best settings for the hyperparameters of a model. But in our case, we kind of short-circuited it and used it as a way to run our tenfold cross-validation on our data sets. So here's our, I want to talk a little bit about the data we have. We have 10 data sets. 9 of them are these experimentally designed situational choice experiments. SP stands for stated preference. In the choice modeling literature, that just means we did a survey. And the other one is revealed preference, which means we built our model based on actual behaviors. It's what's called a patient chart study. Some of my clients, instead of doing surveys and collecting data from doctors, will do what they call a patient chart survey. They'll call the doctor's office and interview a nurse, and they'll ask the nurse, hey, go to the file, pick the last 10 rheumatoid arthritis patients, and tell us how old was that patient, what concomitant conditions did the patient have, what were the patient's vital statistics, what were their previous medications that they might have succeeded or failed on, and what did the doctor prescribe most recently for that patient. So they're using the doctor's actual behavioral data rather than survey data. And in that particular case, there's no experimental design, it's cross-sectional. For each of these 10 data sets, we're going to run the polytomous logit model. We're going to run cart trees, conditional inference forests, random forests, and the catboost method. And we're using tenfold cross-validations and summing our prediction across the folds to get out-of-sample hit rates. That's the method we're going to use for comparing predictive validity. So here's just a summary of our 10 empirical studies. Studies 1 through 9 were experiments. Study 10 was our cross-sectional data. Here's the number of parameters in those in the logit models. And you can see, since we have a vector of coefficients for each level of the outcome variable, the more levels there are in that outcome or that dependent variable, the more parameters we're going to have in the model. And some of these get to be pretty big models. We've got a model with 102 parameters. So they get to be pretty large. Here's the number of respondents in each of my data sets and the number of choices each respondent made. Again, once we get a physician on the telephone, we're typically paying these folks lots of money. We don't want to ask them just one question. We want to get as much value as we can from the interview, so we'll typically ask 8 or 10 or a dozen, or in one of these cases, I think we might have had as many as 16 questions per physician. And then in the patient chart study down there at the bottom, we had each nurse, in each of those interviews, we had the nurse retrieve 5 patient records. And here's the results from our cross-validation analysis. The thing to note is that the catboost model, the one that Joe ran, worked really well. In fact, in every one of our data sets, it had the best prediction. Sometimes just slightly, but sometimes by a much wider margin. But the point is, it always won. So I guess one lesson here is, if you're interested only in prediction, catboost is a really interesting new model. It's a little bit more time-consuming to use, but the use pays off even in these experimentally designed studies where we don't have collinearity and all that nonsense. This should be really well-behaved data, and catboost is still working really well there. So I thought that was kind of interesting. If you just ignore that column and don't pay attention to it, the other methods are, sometimes the logit's winning, sometimes the cart tree is winning. Because of the lack of collinearity, I think that the cart tree is usually working better than the forests are working. The forest's big advantage over cart is their ability to operate well in the face of collinearity, and we don't have any of that. So when it comes to explanation, and I put this slide in here because this is what's important to my clients. They want their models to predict well, of course, but they want to understand what's driving the behaviors. So if I think about those different methods, the trees and the logit model they're really convenient to build into Excel-based simulators. That's what I hand off as a deliverable to all of my clients. Whether they're commercial clients or academic clients, that's one of my main deliverables is an Excel simulator, so that they can play what-if games with the data. What if this had been a slightly younger patient, or what if we could get the patient's blood pressure down? What would the physician's decision be then? And if I can't build it into something in Excel, it's hard for me to deliver that to my clients, because if it's some kind of software that they have to install on their machines, out in corporate America, there's IT departments, and IT departments are powerful, mysterious forces of evil. And I say that to taunt Kurt a little bit, because I know he's got an IT background, but they prevent users from installing software on their machines. So if my clients have to install anything on their machine, they get very nervous about it, because they can't do it, because they have to go pray to the IT gods and hope not to be as disappointed as they expect to be. So that's important in practice, that's important. Random forests produce important measures for the attributes. If you think back to that chart I showed you with the different columns of coefficients, those are very hard to interpret. My academic clients love those because they've got standard errors, and you can turn them into odds ratios, and you can say things like, if we get the patient's blood pressure down a little bit, there'd be a 23% chance less that they'd be put on a certain medication, and that's important. Odds ratios are things that academics talk about. They're not things you talk about to vice presidents of marketing. So my clients, who are lowly market research analysts, don't want to tell their bosses or their bosses' bosses or anyone else inside their organization words like odd ratios or standard error. They just can't have that kind of talk. So they're much happier if I just give them a vector of importances that I can put in a bar chart. But the logit does provide nice interpretable statistical models with coefficients and stat tests and odd ratios and all that good stuff. And the trees provide client-friendly graphical summaries. You saw the tree about the frogs, right? You don't have to look at a lot of numbers or understand much. If you just think about if you look at the tree and see where it's making its splits, you really understand the story. So the trees are better for visualization. So here's my visualization of the results here. When it comes to prediction, catboost is really the winner. When it comes to explanation, though, it's really going to be the other methods. I get importances from the random forests. I get better visualization from the trees. I get a nice statistical model from logit. And from logit or trees, I get a nice Excel simulator that I can give to my clients. So in terms of my practice, although I know that catboost is a winner for prediction, I'm probably going to keep delivering logit models and trees to my clients, because those are the most useful things. But it was fun to look at these other methods as well. And I was a little bit surprised initially that the random forest didn't work better. And then when I thought about the kind of data I had, it was experimental data, experimentally designed data without linearity. That helped me understand why that didn't work so well. And that brings me to a list of references if you're interested in reading more about this stuff. And I think that's it. Any questions? Yes, sir.
You said a few times that your data doesn't have linearity.
Yes.
Can you expound on that?
Yeah.
I don't understand that.
Okay, well, let's go back. So this is what I'm giving my respondents. In the real world, there might be some correlations between these things. It could be that maybe people who are less active are more anxious. So if I looked at real patient records, real humans, I might see some correlations in the data. However, this isn't a real patient. This is a patient that I made up. I went to what's called the fractional factorial design experimental design package, and in my data set, age, gender, body mass index, anxiety level, the patient's smoking behavior, and their activity levels are all perfectly uncorrelated. Correlations of 0.0. Just because I can force my patients to behave nicely and conform to an experimental design, which we can't do with cross-sectional research. Yes, ma'am.
First off, I just really appreciate the fact that you use cross-validation for assessments. I am kind of curious about what you meant by hijacking the current package, and the reason I ask is when I teach the use of cross-validation, I usually advocate for an outer layer of validation around any cross-validation that's used for picker parameter selection. And so I don't use GERT much yet, but I can see the strong benefits, and I'm just kind of curious how you used it.
Well, I might let Joe tag on to my answer here, but the answer is I've never used carrot before either, and I was thinking to myself, oh darn, I'm going to have to make each one of these models and then split the data set into 10 and then run each model 10 times. And I think Joe let me talk like that for a few minutes before he interrupted me and said, no, we're not going to do that. We're going to use carrot because carrot's already built to do the cross-validation for other purposes. We're just going to repurpose it for our needs. Joe, did you want to add to that?
Sure.
I'm sorry.
So I think we did what you're alluding to. We actually did pull a data set out for testing, training data, there, and also training models. So the model was parameter determined there. And then that was applied to tenfold cross-validation. The data set that had nothing to do with the model.
Thank you both.
Any other questions? Yes, sir.
I would really like to learn more about using trees and forests. That's kind of a new thing to me. Any references or resources you recommend, like books, videos, courses?
There's a couple of excellent introductions that you can get on Amazon for like $1 a piece. Just some ebooks. But there's send me. My name is Keith at SawtoothSoftware.com. KEITH. Send me an email. I found a couple of really nice references in R that very clearly lay out the code that's used. Are you an R user?
I'm
Okay. Because I can send you the code too, but I can send you these references, and they really helped me get started because they were just so clearly done that even a novice R user like me was able to use it.
Okay. Yeah.
Sure.
All right, we are out of time now. Thank you, Keith.